Okay, so we're going to go over an example that asks you to actually build up the parameterization. So what's going on here is we have two different circles, one of radius 4, one of radius 6, and a line passing out through those circles at an angle of theta. Now, the x and y coordinates of this point, call it point P, actually both relate to theta and the radii of the circle. So for instance, for the y coordinate here, that's just going to be the height of my point on this circle. So I can put that as a 4 here if you'd like. And for the x coordinate is going to be the hypotenuse of this triangle. And the way that this triangle is drawn is that this radial line intersects the circle at a right angle. Then you take that right angle down to this point on the x-axis, and that's your x-coordinate there. So let's see if we can't find some equations based on these two ideas one at a time. And I think I'll start with the easier one first. That is, let's figure out the y-coordinate. So for the y-coordinate, let me zoom in on this picture a little bit and draw myself another little triangle. So that would look like this. Here, and then here. And let's label things accordingly. So I've got theta here, the radial distance was 4, and I want to know what the y height is. So fortunately for us, we've got a nice right triangle like that. Can anyone think of a trigonometric identity that involves all three labeled parts of my triangle?
Sine.
Sine.
Yeah, the sine. Sure. Perfect. The sine. So the sine of theta is going to be the opposite over the hypotenuse. So it's going to be y divided by 4. Or if you multiply both sides by 4, you get 4 sine of theta for your y coordinate. Yay. All right, so that's half of our problem. We've got part of this defined as theta, or as a function of theta. Now I need to work the same magic with the x coordinate. And there's just a little something to be careful about there, and that is drawing this triangle correctly. And understanding one thing that tripped me up for a moment when I was working on this. So here's our right triangle, this, and there, and that's theta. And let's see, what else do I need? Oh, I need to label this side as 6. And this side is right here. So that's going to be my x-axis. Let me see if I can't do it this way. So I try and color coordinate these things. So the x-axis here and here, the same. I need to know the x-coordinate, which basically means knowing the length of the hypotenuse here. So you look at that and say, okay, well, I want this side. But where you got to be careful is in working with this. This is your right angle. If I look at, say, the cosine of theta, remember SOHCAHTOA? SOHCAHTOA. What's the ka part stand for?
Adjacent over hypotenuse.
Yeah, cosine is adjacent over hypotenuse. So this has to be the adjacent side. And this has to be the hypotenuse, which is x. If you solve for x, you get x cosine of 6 equals, or x cosine of theta equals 6, or x equals 6 divided by cosine of theta. And that's what you're looking for. You wanted x by itself. X is now a function of theta. You've got y as a function of theta. You've got x as a function of theta. Alternatively, you could write this as 6 times 1 over cosine of theta, which is 6 times the secant of theta. I think WebAssign might write their answer like this, but they should accept this. If they didn't accept this, I'd be pretty unhappy. Overall, our point would look like this: 4 sine of theta and 6 secant of theta. Okay. How's example D look? Is that all right?
I'm kind of confused on where you got the lengths for the sides from.
Oh, they have to give that to you in the problem. So that came from my initial drawing. So you're on a circle. The smaller circle is a radius 4. The larger circle is a radius 6. So because it's a circle, that radial distance and this radial distance have to be the same, right? That's what defines a circle. It's distance, a uniform distance from a central point. So that's where I got this as a 4, and this larger one was a 6. Does that help?
Yeah.
Okay, good. Anything else on example D here?
Is your point backwards, or is it just me? Am I just not understanding?
Which one? Here?
The point you made at the bottom, like the XY point.
Oh, maybe. Yeah, I think it's just a video distortion. So let me try and write it again. See if we can't clear up that distortion. So it should be 6 secant theta and 4 sine of theta. So you might be looking through something called a Ludor lens, and they're kind of cool. Ludor lens. They do some interesting stuff. They can make things invisible depending on the background. And here's an example of it. Let me see if I can just show you the. All right. Let's see. I don't want that part.
I like how ready you were.
All right. Oh, don't fade out. Here we go. That's pretty cool. And I'll let you look it up later if you'd like, but I thought that was pretty cool. Has anyone seen that before? Anyways, you can check it out. A Ludor lens. Although I'm not sure if, I think it's spelled Ludor, but it sounds like the pronunciation is Ludor. Okay, let's keep going. Example E. So there's a couple things I want to get out of this example. One is, the big one is showing how to eliminate the parameter, because that's going to become important for us in these types of problems. So we'll start out with x equals sine of 1/2 of theta, and y equals cosine of 1/2 of theta. For negative pi is less than or equal to theta is less than or equal to pi. Okay. So not bad. There's a trick in eliminating the parameter here. And the trick goes back to something that you might do well to recall. And that is sine squared of alpha plus cosine squared of alpha. What does that equal?
1.
1. Thank you. All right, so let's just keep that in mind as we work with this problem. And this will actually get us out of a lot of trouble with a lot of our parametric equations. So what I can do is I can square both sides of this and get x squared equals sine squared of 1/2 of theta, and y squared equals cosine squared of 1/2 of theta.
Are you squaring them?
I'm squaring both sides. So basically I'm saying, okay, let's take, now let's see here. Taking whole thing, sine of theta, or sine of 1/2 of theta, and squaring it. And I'm doing the same thing on the other side, as I'm squaring both sides of the equation. Now, this is just a different way to write what this is. You're squaring the whole function.
But why are you squaring it though?
Ah, great question. Why am I squaring it? Well, my eventual goal is to use this, so that if I add these two equations together, if I take x squared plus y squared, adding their left-hand sides, that would equal sine squared plus cosine squared on the right-hand side. So maybe you can answer your own question now. Do you understand why I squared both sides? What's the advantage of doing that? Does this simplify it all now? Hint, hint.
Does it go to x squared plus y squared equals 1?
Yep. This whole thing is 1. Doesn't matter what alpha is, as long as these two angles are the same. When you square this and square this at the same angle, when you add those together, you're going to get 1. So overall, what we're going to get is x squared plus y squared equals 1. Yay. What's this graph look like? Does anyone remember?
Circle.
Yeah. Circle, radius equals 1, and it has a center where?
0.0.
Good, thank you, 0 and 0. So let's look at that. And I think I have this one on our Desmos link. No, where is it? Let's go. It's 2. Oh, here we go. Yeah, so let me just shut off some other graphs here. That one and this one. And come on back up to this one. So here's our parametric equation. And what I've also got here is this nice nifty little slider. So I'll put this link in the chat here for us if you wanted to play along or look at it afterwards, doesn't matter. Let's see, everyone, there we go. But here's the thing. Oh, did I just delete that? No, I didn't. Whew. All right, let's let's play with this. You can move the parameter, and that's going to show you basically the orientation of this curve, right? So as you move it around, which direction is it going? It's going clockwise. If you move it in the negative direction, it's going to go counterclockwise. No shocker there. So that's the big part of this, is understanding what this graph looks like. When you eliminate the parameter, you've got a circle of radius 1. But then there's another little part. They ask you to look at this for some specific values of the parameter. It's not just -10 to 10. The problem actually asks you to work with this for these parameters, -1, -pi to pi. So then what does it do? Does it trace out the whole graph? If so, in what direction? Let's take a look. So this is doing it the fancy way. You can do it the manual way. Let me take a look at the manual way first and see what that would entail. The manual way would be to decide, well, what happens when I put in pi or -pi? Where does this graph start? So you can make yourself a little table down here, values of theta, our x and y coordinates. So sine of 1/2 theta, cosine of 1/2 theta. Let's see our x and y coordinates. At -pi, plugging that in, that's going to be -pi/2, which is a -90 degrees. So I have x coordinate of -1. Y coordinate is going to be 0 at that point. Another point that you could look at would be, say, at 0 for x, or 0 for theta. That'd be 0 and 1. Cosine of 0 is going to be 1. And finally, up at pi, back to 1 and 0. So is it tracing out everything? I don't know. It does give you an orientation. So let's look back at our graph. I'm just going to change this up to be -pi to pi. So those are my limits. Now notice where it starts out. It starts out on the x-axis. And when I trace it, I don't think I'm going to get everything. Take a look at the little cursor in blue. When I go from -pi to pi, certainly I see the orientation, but do I get the whole circle? Anyone? Did that trace out the whole circle?
No, half of circle.
No. Yeah, just the top half of the circle. And that's what you should be drawing on your paper when you graph this for me on an exam. Is that, okay, you're only going to get part of this, the top half of the circle. So -1, 0, and here to 1, 0. I'll overshot it a little bit. So let's just clean that up. Beautiful. And it got traced out in this direction. Beautiful. All right, so
So,
one more time.
based on these problems, like the examples we've been doing, we don't really need our graph to like know the direction. We can just kind of tell by looking at our points. Correct?
Yeah, you can look at some points. I mean, if you take a look at these, for instance, I was here, then I was here, then I was here. So it was 1, 2, 3. It pretty much tells you which direction the graph is oriented, isn't it?
Sure.
So yeah, you're exactly right. You don't have to necessarily put this in a graphing calculator or a Desmos to be able to figure out the orientation. But I am hoping that it's nice to see it, that it matches what your intuition is telling you and or it matches what the tables are telling you.
But isn't that easy to mess up if you were to go the other way?
What's that?
Isn't that easy to mess up if you were to draw it the other way?
Well, you do want to be careful, because it is easy to get these things mixed up, the orientation mixed up. It's also easy. Now, I didn't take the calc exam that they gave in the most recent version of the AP exams. A lot of high school students took the calc exams this year. But what they did, amongst other things, is they gave out a lot of different versions of the test. And that's something I could do very easily as well. I could give out different versions of the test. Small changes, like if I just put a minus sign here, let's see how that changes this graph. All right, so when I start out graphing this at negative pi, now it starts out here at x equal 1. And as I move the cursor, you can see that it's got a different orientation. Or if I made this negative, then I'm going to get a different part of the graph altogether. Now when I trace out this curve, it goes along the bottom edge of the graph, and again in a different orientation. So there's a lot of subtle things you can do here if you're writing different tests to change it, even though it has the same degree of difficulty. You are changing it, and if somebody feels inclined to share answers, then it becomes obvious pretty quickly. So, but the point is that you want to take and be careful about looking at the orientation of the graph, because that's something that's hopefully an easy couple points in terms of an exam. Did you draw the orientation correctly? I mean, probably if you look at the answer key to this exam, on some of the problems I might say orientation, 2 points. That's nothing big, but it's something that you want to get right. Any other questions on example E?
Thank you.
Yes, yeah, you're most welcome. No, it was a good question, a good discussion. Okay, well, let's jump up to example F, and I think I want to do that one here. All right, so example F, you've got 2 curves, one defined this way, x1, y1, and the other one defined x2, y2. And I want to graph both paths of the particles. Now, I'm going to copy these down, and we're going to think about the graphs not by necessarily graphing them initially, but by eliminating the parameter and just seeing, well, what's it look like in x and y? And that's how we're going to approach this. So if you want to copy that down, right now, I'm going to be doing likewise onto my paper here. This is example F. So here's our 2 functions. And what I want to do is I want to try and play with these things and eliminate the parameters from them. So from the first one, let's see, let me do the second one. What I'm going to do is I'm going to move the 2 to the other side and get x plus 2 equals cosine of t. At the same time, I'll move the 1 to the other side. I'm dropping the y2 and x2. But y minus 1 equals sine of t. Now, one way, I guess, to eliminate the parameter would be to solve for t. You could take the inverse cosine of this. That's a really painful way to go. There's a trick that we used in the last problem. Can anyone see what you think I should do here?
Square it.
Square it. X plus 2 squared equals cosine squared. Y minus 1 squared equals sine squared. So perfect. Thank you. And then if we add these together, I get x plus 2 squared plus y minus 1 squared equals cosine squared plus sine squared, and that equals 1. So yay, I got rid of my parameter from the first one. And I get this, x plus 2 squared plus y minus 1 squared equals 1. What's the center of this circle? I'll help you out with the radius. Radius is the square root of 1, which is 1.
-2 and 1.
Thank you. -2 and 1. Okay, perfect. Let's turn our attention to this other one. And we'll play kind of the same game here. So it's going to be x squared equals 4 sine squared of t. Y squared equals 4 cosine squared of t. So, all right. Looking okay here. We can combine things like we did with the previous problem. I'm going to do x squared plus y squared. That's going to be 4 sine squared of t plus 4 cosine squared of t. But that doesn't look like 1. What can I do here?
Factor out of 4.
Factor out of 4. Yeah. If you factor out of 4, you'll see pretty quickly that that term disappears here. That becomes a 1. So we've got another circle. We've got 2 circles. We got a circle with a center at -2 and 1. And this one has a center at 0, 0 with a radius equal to 2. So some good practice in eliminating the parameter there. Let's take a look at these graphs. And there's a couple follow-up questions here. Oh, it's this one. Okay, so here's my 2 equations. And let me zoom in on them. Now, the first follow-up question that they asked you was, how many points of intersection are there in these 2 graphs? Now, I didn't need to draw a dotted graph. I just did that so you could distinguish the 2, but draw this as a solid graph. There you go. How many points of intersection are there in these 2 graphs?
2.
2. So 2 points of intersection. All right, so there's a quick couple points for you on web assign. 2 points of intersection. Did I share this link with you guys? Do you have this one?
Yes, we do.
Okay, thanks. So here's the cool part. And you can unmute yourselves so I can hear you go, ooh, ah, because this is really cool. Let's first of all crank this all the way over to 0.
Ooh.
Now, don't wait. The cool part's gonna come. And then turn on these 2 equations. You should see a blue dot and a black dot. Now, what they're looking for is what's called a collision point. They want to see, is there a point where these two points, as they're moving around in accordance with our parameter, do they collide? So here you go. Ready? Now you can go, ooh, ah.
Ooh.
Yeah, there you go. So, it's looking bad. Bam! Distracted driving, man. Sue him. Get Mike Morris, right? Or Jeffrey Feiger. All right, but there's a collision right there. So there's one collision point. So do you understand what I mean by collision point? That these curves are parameterized so that they're at the same place at the same time. Now, how about the other one? Do you think they're going to hit again?
Hope so.
Yeah, I know. I was disappointed. So there's 2 intersection points, but only 1 collision point. Only 1 collision point. So do you see the difference between an intersection point and a collision point? Okay. I hope so. So, bam, right there. There's your collision point. I think they have another question here. So there's your collision point. Now they wanted the coordinates, so we can just look back and see the coordinates. The coordinates of the collision point are right here at -2, and it doesn't look like quite 0. But it's -2 and 0. There was another question here.
Is there a better way to do that?
So yeah, I was thinking about that in association with this last question. It goes, if the x and y coordinate of the second particle is given by x = 2 plus cosine of t, instead, is there still a collision? So for that part, let's see. I want to shut off this graph here. And I want to turn on, let's see, it's going to be this graph. No. Well, that's our point, but I think this is the graph. Yeah. So if you shut off this one graph above here, and we'll use this point and this graph, let's rotate around and see if there's a collision point again. So let me go all the way back to 0. And I guess there's one other point I can shut off here, and that would be this one. Let's see if there's another collision point. No, nothing there, nothing there. So you can go all the way around here, but there's no other collision point. But that's visual, and that'd probably take a little bit of talent with Desmos that you absolutely do not need to have. So the good question that followed this up was, well, how do I tell? And let's see here. Example. Yeah. So in order for there to be a collision point, the X and Y coordinates have to be the same at a particular value of t, right? So at time 3/4 pi, the X and Y coordinates have to be the same for both curves. That's what has to happen. So let's see here. Let's take a look at what that would mean for our particular problem. For our particular problem, the X coordinates would be these two. Those would have to be the same at some point. So collision point. Let's see. So x1 equals x2 would mean 2 sine of t would equal -2 plus cosine of t, like that. And then the y coordinates would be the same, kind of means something similar. So coming back up at the top, that would mean this has to be this. So let's compare those two. So that's going to be 2 cosine of t equals 1 plus sine of t. Okay. Let me move all this to one side, and I'm going to create a new function. So it's going to be 2 sine of t plus 2 minus cosine of t. I'll call that, say, f of t. And this I'll call g of t. I'll move this to the other side. 2 cosine of t minus 1 minus sine of t. Now, in order for these things to be equal, this would have to be 0, and this would have to be 0. Both these graphs would have to be 0 at the same time. And you can actually just look and see where that happens. So here's the graph of the first one for your x coordinates. Is that right? Cosine of x. And here's the graph of the second one for your y coordinates. And what you're looking for is where they're both 0 at the same time. So let me kind of zoom out a little bit so you can see a little bit more of this repeating pattern. But there's not too many places where they're both 0. They're both 0 here, and they're both 0 here, but they're not both 0 here. Only one of them 0. So at every 3 pi over 2 plus or minus multiples of 2 pi, you're going to see a place where they both cross. So 3 pi over 2, let's get a nice numerical value for that. 3 pi over 2. There you go, about 4.712. If you look back to our little demonstration at about 4.72 for C, I think that's where we saw that they were both about equal. Yeah, right there. So that's what's going on with that. That's probably a little bit longer of a problem than I would put on an exam, but I did want you to see what you can do to try and figure out solving that without necessarily having to have a lot of Desmos skills. So you'd set the x and y terms equal to each other and look for where they're both equal at the same time. This one was kind of hard. A lot of them aren't quite that hard when you're looking for that point of intersection. All right. Let's do one last one, then we'll take a break. Is there any more follow-up on this one? All right. Seems like everyone's happy to put that one behind them. So let's move on to the last example.
Oh,
Which is-
what was the other point when we did all that?
So there's actually only 1 point in the interval 0 to 2 pi, and that was 3 pi over 2. So the other solution didn't turn out to be in that interval. So in the interval 0 to 2 pi, there's only 1 collision point. Now, if you do go further outside this, you know, once you get to 3 pi over 2, which is about right here, every 2 pi beyond this, you'll see another collision point. Kind of almost looks like Mickey Mouse there. I'll look at it. All right, but did that answer your question?
Yeah, it did.
Okay, thank you. So let me go back to this one here. And this talks about a projectile fired with an initial velocity of v0 meters per second at an angle alpha above the horizon. Basically, if you shoot something or throw something, these are the parametric equations that tell you its position. Now, here we're not accounting for air resistance. That would make these equations more complicated, but they give you the values that you need. Alpha is 30 degrees. Okay, so that makes this x equals v0, and v0 in this case is 600. So let's try 600 cosine of 30 times t. And the y coordinate is v0 again. So it's going to be 600 sine of 30 times t.
I'm sorry. Did you say not?
Not. Yeah, I'm sorry. It's just
Thank
a
you.
habit. I had an English professor one time, and they referred to this as not versus sub-zero. So yeah, not is an N-A-U-G-H-T. Basically, it's V sub-zero. So thank you. Minus 1/2 of g. Now g they give us is 9.8 meters per second squared. That's the force of gravity. So 1/2 times 9.8 t squared. So as I was solving this the other day, I guess it's my habit from my physics class that g is 9.81 meters per second squared. And I kept on getting off. You know, my final answers weren't matching this. I was going crazy. Finally, I figured out that you didn't use as much accuracy as I did. So, all right. So the first thing to do is to figure out if the gun is fired, when is the bullet going to hit the ground? So let's take a look at, first of all, our equations with V0 is 600 and G is 9.81 or 9.8 meters per second
Are you writing something?
squared. Not really, just copying down the problem.
Okay.
But now we got to get to writing something. Let me rewrite that as 4.9. And we can also simplify our equations a little bit, in particular the y equation, because sine of theta is 1/2 and cosine of theta is square root of 3/2. So that gives me some more friendly equations to look at. That's going to be x is 300 times the square root of 3 times t, and y is going to be 1/2 of 600 is 300, t minus 4.9 t squared. So this thing's going to travel quite a ways, or for at least a long time, relatively speaking. You want to know, when's this thing going to hit the ground? Well, good question. When does it hit the ground? Well, that's going to be determined by the y height. And the y height on the ground is going to be what?
0.
0. So if you said 0 equal to 300 t minus 4.9 t squared, I'm hoping that your algebra skills hasn't left you. You factor out a t, and you get two possibilities, right? Because you got something times something is 0. Either t would be 0, or 300 minus 4.9 t equals 0. T equals 0 when it's initially fired. This equals 0 when it's going to hit the ground. So this is going to be 300 divided by 4.9 equals t. Rounding off to the nearest second for WebAssign, it's about 61 seconds. 61.22, but then again, WebAssign wants it rounded. So there's the answer to our first part. We're okay with when it hits the ground.
Yes.
The second part is how far from the gun will it hit the ground? Well, we want to go back to our equations again. Figure out basically how far your projectile is going to go. And it's going to travel, for 61 seconds. And I'm kind of curious here because I think I've forgotten. Now the exact answer here, or more of an exact answer, is 61.16. And I think I got to use that to find part B. How far will it travel? Well, how far it travels is going to be given by the x coordinate. So let's figure out what that is. I've got x equals 300 times the square root of 3 times t. But we're going to take this value of t and plug it in here. So 300 square root of 3 times 61.16. And that's a calculator problem. I'm not going to even pretend to do that one in my head. So 300 times 61.16 times the square root of 3. Let's see if this matches what they have in the book. No, not quite. I wonder. That's a little bit better. Let me try something here, because I'm not getting from my calculator exactly what the book got or what WebAssign got.
300 divided by 4.9 is more like 61.22.
Yeah, that's what I was thinking. I think I must have got the wrong value there. Yeah, in fact, I don't know where I got the 22.
I inputted that long decimal it gave me for part 1, and then it gave me that number for the second part.
So here's what we'll do. We'll take 300 divided by 4.9, and I'll hit the store key. I'm going to store that in X. Now, if you're still in parametric mode, or probably store it in T, that's fine. But I'm going to take this. You know what? You just hit the times key. Times 300 square roots of 3. Oops. 2, 3. There you go. That's now matching what I got from WebAssign. So it should be a 22, 3181, 3.17, etc. But again, kind of like the last one, they want it rounded to the nearest integer anyways. So 31813, and that'd be meters.
Where did you get the 300 root 3 from?
Oh, back up here. our original equation was 600 times the cosine of 30. Cosine of 30 is the square root of 3 over 2. If 2 cancels into the 600, that leaves you with 300 times the square root of 3.
I see. Okay.
Appreciate you asking. Are we good with how far? All right, let's keep going. Next question, what's the maximum height reached by the bullet? So the maximum height is going to be the height of the bullet halfway through, all right? Halfway through its flight. So basically what we need to do is we need to take and figure out its height at the right time, which would be 30.6 something seconds. All right, so let's see, I think I stored that value in X. That's how long it takes to do the entire flight, right? So that's roughly speaking, here's what your flight's gonna look like. So it was 61.22 seconds later. The maximum height is going to be reached at the midpoint here. So I need to take this and divide it by 2. I've got the full value right here. So I'll take and divide that by 2. And now I just want to find the y coordinate at that point. So our maximum height let's see, that's going to be y equals 600. Actually, you know what? I should use the simplified equations. Half of that is going to be 300 t, oh, here we go, minus 4.9 t squared. So let's plug that in and finish this part up. 330.61 minus 4.9 times 30.61 squared. I'm going to use my store key again because it's absolutely convenient to do so. You don't have to. Store in X. The nice thing though is that you're probably less likely to run into an error that your answer was off by enough that WebAssign marked it wrong. So if you hit the store key and then this key, that should store it. Let's clear out my calculator and then type in this equation. It's going to be 300 times x squared minus 4 point, excuse me, no, not x squared. My bad, let me start over again. 300 times x minus 4.9 x squared. There you go. So about 4,592. Okay, 3 down and 1 to go.
And I just have a quick question. If it's like, let's say 8,163.265, is it going to want 1864?
0.3625. It's going to round it up to the nearest whole number.
Okay, got it.
This problem.
Thank you.
Mm-hmm. And I think there was the last problem. Find the equation of the path of the particle represented by eliminating the parameter. All right, so what you need to do in this one is solve for t and then plug it in and see if you can't clean things up. So the easiest thing to do to solve for t would be to solve for t from this part right here. Or actually, maybe this part right here. So I'll kind of get you started on that and let you finish the rest because they can't randomize this part of the question. T equals x divided by 300 times the square root of 3. And I want to plug that into here. So it's going to be y equals 300 times, I'll call it 300 over 1 times x over 300 square root of 3. You know what? I can't do that. I'm sorry. I'm so sorry. I think it's going to want things done more generally than this. Yeah. It wants things done in terms of sines and cosines. So my bad. This would have worked for our particular equation, but if you want to do it in general, we got to go back to this x equals v naught sine of alpha, no, v naught cosine of alpha times t. I'm starting to feel really bad here. I know I want to get you on a break. T y equals v naught sine of alpha times t minus 1/2 gt squared. So let's just talk through this a little bit. T is going to be v naught cosine of alpha. We're going to take that and plug that in here. Well, when you do that, the v naughts are going to cancel each other out, and you'll have a sine of alpha over cosine of alpha. And the sine over the cosine is going to give you a tangent. So what we'll be left with here is x tangent of alpha. 1/2 g and t squared, that's just going to be x over v naught cosine of alpha. And I think, am I missing another v naught here? No. So you're almost done. This gets squared. And let me remind you that when you have a cosine in the denominator, cosine, 1 over cosine is equal to secant. So almost done right here. Just do a little bit of extra thinking to finish this one up in WebAssign. Whew. All right, hope you're still with me. If you are, great. If not, if you have a little quick question on something, fire away. All right. No one wants to be that guy. Go ahead.
Where'd you get the tangent from?
Where'd I get what?
Tangent.
Oh, when you plug this into here, what you'll end up with is a v naught sine of alpha, and then the x v naught cosine of alpha. The v naughts will cancel. You'll end up with sine over cosine. That'll give you the tangent. So you're just substituting in for this into here for t. I didn't show it, but it'll happen. I'm kind of leaving a little bit for you guys to work on in the homework. Anything else? All right, we'll stop here.